4. So up until this point, we have talked, thank you the 11 folks that say on page 4 in our packet. Ozzy, turn around, page 4. Here we go, page 4. We've talked a lot about different kinds of reactions. We know the types of reactions, we know how to write and balance those reactions, we know how to do calculations with those reactions. We're going to spend this unit, about 2.5 weeks long, looking at how energy and heat move and change across a reaction. Every reaction does two things. They are breaking chemical bonds. This absorbs energy. It takes energy to break a bond. Filling in page 4. And we are releasing energy, forming new bonds. Every reaction does both of these things. But we classify reactions based on what they do more of over the course of the reaction happening. That is either endo or exothermic. Right underneath this, you should see a T-chart. We're going to fill that in momentarily. Right. Endothermic reactions, so a couple of things that are important about them. They absorb energy. They are taking that energy and sucking it in for these chemical bonds. They also feel cold. So when you've ever used an ice pack, you're like, oh, miss, I hurt myself at lunch, I need an ice pack. You take the ice pack, you crack it. Gentlemen. That cracking of the ice pack causes a reaction that sucks the heat out of the world around it, making it nice and cold, which then feels great on your hurt knee, your hurt face, whatever you do to yourself. In these kinds of reactions, heat is a reactant. It's getting sucked in to form these new chemicals. Exothermic is the opposite. So what happens to the energy in an exothermic reaction?
Escapes.
It escapes. It's going to be released out into the world. How does it feel? Hot. And then where would the energy be? If it's not a reactant, it has to be a product.
Oh, that's why it has the prefix, right?
Yep.
Endo, Endo.
Fire is a good example of an exothermic reaction, releasing that heat out into the world. Once you captured all this in the T-chart, pull out your tiny table, your tiny periodic table. This guy. Tiny table. We're going to spend the whole rest of the semester on this part of our semester. Probably do more for now. If you have lost your copy, I am out of copies, but I will have more tomorrow. Once we enter. 15 more seconds. Find your tiny table wherever it exists in your backpack.
So you're just the opposite from each other. Once you have your tiny table, I'm going to model something real fast, and then we'll highlight something on our tiny table. Once you have your tiny table, please have your hands free. This is one of those weird things that we do. You're like, oh God, Miss, let's do this awkward thing, but then you use it on quizzes and tests. You're like, damn it, Donovan, it worked. So, hands free. Oh. Endo and exothermic are super easy to mess up because the words are really similar. It's really easy to get those confused. When I'm endothermic, what's happening to that energy? It's getting absorbed. So point to yourself. It's getting sucked into those chemical bonds. Exothermic, what happens? It releases, so it gets out to the world. Show me endo. Show me exo. Endo. Endo. Oh my God, people. Exo. Endo. Exo. Exo. Love it. People are like, oh, Miss, we move our hands around awkwardly. It's great. But your little quizzes be like, wait, okay, I promise it'll happen. If you will, look at the very bottom of page 4. These are the ways we qualitatively look at the observations we can make to see what there's endo or exothermic. But there's ways we can quantify it, numbers we can attach to it. And that's called enthalpy. Whole class, enthalpy. Enthalpy.
One more time, enthalpy.
Enthalpy.
Enthalpy is also called the heat of reaction. We're measuring the change in that heat, in that energy, over the course of the reaction. We've seen this delta before. What did we use delta for before now?
Water.
Heat in a reaction. I'm burning a chemical reaction. You saw this guy before. But you've also seen delta represent change in like your math classes before now. Change in time, change in place. Next year in pre-cal and physics, you'll see delta used a bunch in your calculations. It is just change. Change is always the end minus the beginning to see what kind of change happens. So here, the end is the products minus the beginning, the reactants. Find this equation on the bottom right on your tiny table. Highlight, circle, star this equation. There is always somebody on every test who's like, Miss, I am a rock star, I know all the things by heart, I am so smart, it is totally reactants minus products. And then they are wrong, and they get it wrong, and then they are sad. Your brain has better things to do than memorize this, just look it up.
So now just the opposite. Should from products.
Always the end minus the beginning.
Oh, the end minus the
Any change is always end minus beginning. Once you've highlighted, circled, starred this guy, flip over to page 5. Page 5. You should see graphs. So looking at page 5, you should see 2 camel graphs. It's a highly scientific term. These are the only 2 graphs that exist when it comes to energy. Any other graph shapes that you see that aren't a camel like this are not a real thing. Why did you do this? Why are you eating this?
Oh, it was my water.
Every time you see a graph like this, there are 4 annotations you have to put on there to know what's happening. We need to know where the reactants are, where the products are, if it's absorbing or releasing that energy, and where that enthalpy, where that change in the heat is coming from. Are reactants the beginning, middle, or end? Reactants. Where are reactants? Beginning, middle, or end?
Beginning.
Beginning. So this part here is our reactants. Products are beginning, middle, or end? The end. So the very beginning of our graph is the reactants, the end is always our products. This middle part is called activation energy, but you don't care. I now want to know if this is absorbing or releasing energy. What's happening in this graph?
It goes up.
It goes up. So am I absorbing energy or releasing energy?
Absorbing.
Absorbing. I'm taking that energy in, I get more energy. So draw the arrow going up and write absorb. Last thing, we need to know where that delta H, where the enthalpy is on this reaction. We know it's the end minus the beginning. So it's the difference between these 2 spaces here. So I draw a line at the high point under our products and go down to about where the reactants finish. And this is my delta H, my enthalpy. That's an H. You should annotate this on every single graph you encounter all of the time. It's worth points in your quiz, it's worth points in your free response. So these are annotations. So let's actually calculate this. Right underneath this you have a space that says delta H equals. We saw that calculation a second ago. What is the calculation for delta H? What minus what?
Products minus reactants.
Okay. Products minus the reactants. So let's fill this in. Our products hit at about 350 kilojoules. Minus the beginning, our reactants, 200 kilojoules. Equals positive 150 kilojoules. And this makes sense, because if I'm absorbing energy, I should have more at the end than I did at the beginning, so I should have a positive change over the course of a reaction.
That's 350.
350 minus 200 is positive 150. Yes, the units are important. Do keep the units. They always come from that y-axis. KJ. Once you capture this with your neighbors, take 2 minutes. Do the same process on that second graph. Reactants, products, is it absorbing or releasing? Where is the delta H? What is the delta H?
Just read that to
Say it again?
KJ.
Because it comes, oh, yours doesn't say it. It should say KJ here. So it says KJ? It should say KJ. I don't know why it doesn't. It's very weird. Questions? Yeah, so then what's it doing? Reactions either absorb or. What else do you have? Reactants, products, is it absorbing or releasing? Where is the delta H? And what is the delta H? Love it. Make sure you label the delta H, where that space. So this is equal to delta H. So that's the 0 to the positive, right? Difference between these 2 ones. That's this, right? And then make sure you have the KJ here. Yeah. That's okay. X. Because it's still the difference. So I find the high point. So we made the high point. Stop.
Oh, wait, where's the high point?
About 15 more seconds. We're going to call folks to share out their annotations. All right, for our annotations. Boss.
Game.
For annotations, can we hear from? Someone, what should go where on this graph?
What's up? You put R, like then you put P at the bar. You can do an arrow going down, right?
Uh-huh.
Then put release.
Love it.
Is that it?
And then where's the delta H? From where to where?
What?
From where to where is my delta H, man?
Oh, it goes from R to.
So draw a line at 40, draw a line going down, stopping wherever the products are. And then label this the delta H. If you had all of this, put a little smiley face on the side, you would earn full credit for your annotations. And then to calculate our delta H, can we hear from? Ramel, what should this calculation look like? It is a negative number. People always see negatives and they freak out. They're like, oh my god, this isn't wrong, this direction is that. It's okay. If I am giving away energy, I should end up with less than I had at the beginning, which is a negative change. I've given this energy away to people. Make sure you have your unit. Once you have this all filled in and beautiful, go and flip over. Pages 6 and 7 of your homework. Yes, it's 2 pages. No, I don't feel bad. Flip the pictures. And then flip over to page 8. Page 8. Go to what? Page 8 is the unit.